Hello. So welcome back to another week. All right. So in this today's section, we look at two sections, 10.4 and 10.5. So 10.4 focus on the connectivity of graph. All right. So here are a few homework problems that you can try. All right. So when we talk about connectivity of graph, we focus on what is called a path. Right. So there's a formal definition and informal definition. So let's take a look at a formal definition. So a path is technically a sequence of edges that begin at a vertex of a graph and travel from vertex to vertex, right? So travel from vertex to vertex along the edges of the graph, right? So that's the formal definitions, right? So kind of visiting the borders along the way, right? So there's a numbers problem can be modeled. For example, you can see our communication between like one person to another person when they make a phone call, right? That's a path, right? Or you can send a message, right? Things like that, right? A lot of application of path. So here is the formal definition. All right, so let me have a non. So we have a non-negative integer, and G can be any undirected graph. So a path of length n from U to V is a sequence of n edges, right? So we call that E1, E2, En. And then you start the sequence at, upon U, which is x0, and you could travel along the way, all the way to point V, which is xn. And those are the endpoints of that, all right? So, if you can find a connectivity between two vertices, that's a path, right? That's the idea. All right. So we have like a simple path or not a simple path and so on. Um, so we're gonna take a look at a few of those. A path is considered a circus if it begins and ends at the same vertex, right? Where the length is bigger than 0, right? Because you don't want to start upon U and you end upon U, right? That's kind of boring. So if it begins and ends at the same vertex, then it's considered to be a circus. If it's not, it's just a path, right? So a path or a circus is simple if it does not contain the same edge more than once, right? So you can have a simple path when it doesn't contain the edge more than once. Same thing with simple circus, right? So it's travel and go back and doesn't repeat the cycle. That's what we call a simple circus. And this, we can use this to extend to directed graph also, right? So here's the example. So suppose we have a simple graph here, right? There's no multi-graph, there's no loop, it's just a simple graph as we define in section 10.1. So okay, let's see if we can find a simple path of length 4. Okay, a simple path of length 4. So yeah, so pick any vertex that you prefer as long as you can find a path of length 4, and that's one of the example. So suppose we start at vertex B, and then you travel to C, so that's length 1, and then you travel to E, that's length 2, all right, and then you travel to length A, that's length 3, and you travel to D, that's length 4. Remember, it's a simple path, right? So you don't want to repeat the same vertex. So that's the simple path of length 4. So you can see here, we'll start with B. So B, C, E, A, and then D is a simple path of length 4. All right. Yeah. So you don't have to pick the vertex B. You can pick out the vertices, and then you can also find the simple path of length 4. So for example, I can start with vertex A, and I travel along to get to vertex E, travel to get vertex C, travel to get vertex B, and then back to vertex D. That's also a simple path of length 4. Or A, E, C, B, D is also a simple path of length 4. Okay, yeah. So there's a few options that you can have here. So not a path, right? So not a path means that you cannot have connectivity between those things, which is not a path, right? So you can see here that A, D, E is not a path. Just one example, right? Because yeah, you can go from A to D, but then what next? Well, there's no edges connect D and E, right? Because there is no edge connect D and E. So that's not a path, right? That's just one example. You can find like, okay, D, B, E is also not a path, right? That's just one of the example. Now we want to find a circuit of length 4. Okay, we want to find a circuit of length 4. All right, so remember a circuit is you start and end at the same vertex. So you need to find a circuit of length 4. So you can go there and then come back at the same vertex. So I can see here that I can start at vertex A. I travel to D. I travel to B, that's length 2. I travel to C to E, that's length 3. And I go back to A, that's length 4. That's the circuit of length 4. So A, D, B, E, A is a circuit of length 4. Right? If you travel along that direction, right? A, D, B, E, A. So it's a circle of length 4. So it does go back to A. You can see a path of length 4 is B, C, E, A, D. It doesn't go back to A, or doesn't go back to B. So a circuit, you need to go back to where you're starting. So that's just one of the examples you can see. All right, sounds good. All right. So a path, but it's not a simple path. So again, a path but not simple path, you mean that you can go back to that one again. So I can start at, C, E, B, C, and then E, right? I start at C, I go back to E, I go back to B, I go back to C, and then I go back to E again. So this is a path, but not simple. So it's not a circus because I start at C, but I end at E. I don't end at C, I end at C. So it's not a circuit. So it's just a path. All right. So that's a path, but not simple, because you can see that we went through CE twice. Okay. So that's not simple. Simple means that you only across this one, right? So that's the different example we can see. All right. So now we look at another example. So for example, when we have a quantum shift graph, a path exists when between two people, if there's a chain of people linking these two people together, right? So here's the Facebook example that we can have. So there's a lot of options here, but you can see that if we consider Kamini and then Jing, it is there's a chain of 6 people linking Kamini and Jing. Right, you can see here Kamini go to Chen go to Paula go to Todd, and Todd to Camlet, and then Camlet to Jing, and vice versa. So you know, it's an acquaintanceship graph, right? So just the application where we see it in real life. So now we look at the connectedness in an undirected graph, right? So how do we define if the graph is connected or not connected? So a path is different. So now a connected graph is different, all right? So a connected graph depends on the definition of the path. So in undirected graph, it's called connected if there is a path between every pair of vertices. Otherwise, it's called disconnected, meaning that if I pick 2 random vertices, there have to be a connection between those 2. So therefore, it's considered to be a connected graph, right? It doesn't have to be any length, but as long as can I travel from one vertex to another vertex. If I can, then I have myself a connected graph. If not, then it's not a connected graph, right? So not just one pair or 2 pair, every pair of vertices has to be connected, right? So if the graph is not connected, then it is disconnected, right? And we can disconnect a graph by removing vertices or edges above to produce a disconnected subgraph, right? So you can see here, I give you 2 graphs, G1 and G2. So you can see that in G1, you can pick any pair of vertices. We can find a path to go there. So for example, you pick G and E, all right? You can see that G and E are not connected directly, but then G can go to F, to go to D, and go to E. So they are connected. You pick A and G, for example, pick A and G. You can see that A and G not connected directly, but you can find a path to go to A, to C, to F, and then to G. So every single pair of the vertex in the graph G has a path to go there. So therefore, G1 is connected. All right. However, you can see G2 is not connected because I said, well, if I pick D and B, there's no way for me to go to B to D. So therefore, G2 is not connected, but G1 does. All right, makes sense. All right. All right, so that's the difference between connected graph and disconnected graph on that. Now we focus on connected components. All right, a connected component of a graph G is a connected subgraph of G that is not a proper subgraph of another connected subgraph. So you watch the language here. What does that mean? It means that if we have a graph G and a component considered to be a connected component, if they are independent from other components. Okay, so 3 components are all independent from each other. So you can think of there's 3 people working on the same project, but none of them depend on the other to do the work. So that's the idea of connecting components, right? So that's a concept. And a graph G that is not connected has 2 components or more connected components at disjoint and have G as their union. So you can have a bigger graph where they have more than 1 connecting component. Consider that's the union of all those graphs. So here's the example. So you can see here we have 3 connected components. They all independent for each other. You can see here ABC is 1 component. It doesn't depend on any other component. And H2, you have D and E, doesn't depend on the other 2. Same thing with H3. So these 3 connecting component, the subgraph of the bigger graph, which is the graph H. but they all independent from each other. So they call connected component. All right. And that union will create a graph H. So the same thing as three people working on independent projects, but when then combined together, they get the work done, right? That's the idea on that. So now we look at what is called a cut vertices. So the removal from a graph of a vertex and all incident edges produce a subgraph with more, all right, with more connected component than the original one. We call that the cut vertices. And we also have what is called the cut edges. It's the same thing. But now we don't remove a vertex, we just remove an edge to produce a subgraph with more component connected than the original one. And we call that cut edges of the bridge. Excuse me. All right, so when you remove a vertex, you also remove every edges incident with that. But when you remove an edge, you don't remove a vertex, right? That's the difference. All right. So here are two examples. So let's find all the cut vertices and cut edges if it's possible. All right, you can see, take a look at a graph A. So let's say I remove A, right? Remove vertex A. If I remove vertex A, so if I take A away, then means that I need to take this edge away, right? All the edge incident with it. So now how many connected components do you see? Just one, right? So I remove that, then you still have one connecting component. So it doesn't work. So A is not a cut vertex. Let's say we remove D, right? Remove D. So now we remove D. Then when you remove D, you also remove this edge and this edge. Now look at the remaining, you still have one component. So it doesn't do any job. So similar with E and F and B, right? But however, if we are removing C, what happens if we remove C? So if we remove C, then we also take away this edge, this edge, this edge, and this edge. Now you look at the leftover, we actually have two components. So therefore, C is a cut vertex. All right. All right. So C is a cut vertex. Okay. So C is the cut vertex. All right. So now let's see if we have any cut edges. All right. So let's remove HAB. We still have one component. If we remove HAC, we still have one component. If we remove HBC, we still have one component. DC, we still have one component. And DF, we still have one component. And EF, we still have one component. And then CG, we still have one component. So the graph is not really separated itself. So we have no remove edges for the graph A. Make sense? So no cut edges. Now moving on to B. All right, so let's take a look at the cut vertex first. All right, so if you cut vertex A, it doesn't make a difference. It's still one component. If you cut vertex B, then you have two components now, right? Vertex A by itself and the rest. So B is a cut vertex. Is there more? All right, if you remove vertex C, then now you kind of separate the graph into, three components, right? You have A, B here, you have a D here, and you have this guy, right? Three components. So B or C also a cut vertex. All right, so that's the idea of cut vertex. If you remove this guy E, then you take that away, you take that away, you take that away, you take that away. Now you create more component than the original graph. So E also a cut vertex. So B, you see we have more cut vertices than A. All right, so the cut vertices in graph B will be B, C, E, I, because remove those will create more component than the original graph. All right. Now, how about cut edges? So if you remove HAB, you do create two components. Yes. If you remove HBC, you also create two components. You remove CE, you also create two components. You move CD, you still create two components. Yeah, so there's quite a number of cut edges in graph B also compared to the graph A. Okay, so AB, BC, CD, CE, EI, and HI are the cut edges. All right. FG is not a cut edge because when you remove FG, you still have one component. So that's the idea. So same with EG. So when you remove EG, it's still one component. So those are not cut edges. Yeah, so that's the idea. Okay. Now we look at connecting an indirect graph. So indirect graph, we have a strong connective versus a weak connective, because direct graph is have direction. It's not like undirected graph when you can move freely. Okay, so in a directed graph, a graph considered to be a strongly connective if there is a path from A to B and a path from B to A, whenever A and B are vertices in the graph, right? So because directed graph need direction, so if you can go A to B, then if you have a path from B to A, then that's the strongly connected. Otherwise, it's not. All right. And if the graph is not strongly connected, then it's become a weakly connected. So how do we define a weakly connected? Directly. So a directed graph is weakly connected if there is a path between every two vertices in the undirected graph, meaning that if we ignore all the arrow, go from A to B or C to A, then you can still find a path, then it's become a weakly connected. So strongly connected, we have to look at the direction. Weakly connected, we ignore the direction. And can we still find a path between two vertices? Okay, so that's the idea of weak connected and strongly connected on that, right? So meaning that a strongly connected is also a weakly connected, because if you throw away all the arrow in a strong connected graph, it just become an undirected graph. So it's also a weakly connected, but the reverse is not true. Okay, so strongly connected is also weakly connected, but weakly connected is not strongly connected. All right. So that's the idea. So here's the example. So we have here is two graphs, G and H, right? So we can see whether the graph G is strongly connected or weakly connected. All right, so you can pick any path, right? For example, A to B, right? So we can go. Can we go A to B? Yeah. So A to B works. How about B to A? So B to A. So I cannot go directly from B to A as I would do it for A to B. However, I can go from B to D to E and then back to A. Yes. So B travel to D and then travel to E and travel back to A. So there's a path. All right. You can pick anything, right? Let's try another one. How about B to C? Yes, I can go B to C easily. How about C to B? So C to B, I cannot go back in that matter, but I can go from C to D to E to A to B and then back to B right there. Okay, C, D, E, A, and B. So yes, I can go from C to D to E to A and then B. It doesn't have to be, direct relationship, but I can go to a different vertex and still go back to B. So that's the idea of strongly connected graph. All right. Versus you can see here in the graph H, can I go back to B to A? B to A, yes. About A to B? Well, is there a way we can go from A to B? The answer is no. Right, you can see here I cannot go from A to E. E only can go E to A, not A to E. So A to B is no. So this one here is not strongly connected. But if you ignore all the arrow, yes, if you ignore all the arrow, then you can see here I can go A to B and then B to A easily. So that's the idea of weakly connected, right? So if you ignore all the arrow, can you still find a path? Then if you can, then it's weakly connected, right? So that's the concept of strong connected graph and then weak connected graph in a directed graph, right? Undirected, we don't worry about where the arrow has to be, things like that. Okay. And we said any strong connective is also a weak connected graph, right? That I mentioned before. Okay, so G is a strong connective and H is not a strong connective, but it's weakly connected, right? All right, so now we can use path and circus to help us to define whether two graphs are isomorphic or not. So we talked about isomorphic graph in the previous section, 10.3. So before we just solely based on definitions of isomorphic, now we can use the concept of path and circus. So you can consider if two graphs are isomorphic, then they have to be the same. So they should have the same number of paths, they should have the same number of circles, and so on, right? So let's visit this example again. So suppose I have this graph G and H right here. All right, so you can see that G have 6 vertices, so does H. And then let's see, this one degree 2, this one degree 2, degree 2, degree 2, 3 here. Yeah, so graph G have 2 vertices of degree 2, so same thing with H, right? And then graph G have 4 vertices of degree 3, so does the graph H. So you can see that they pretty much the same number of vertices, number of edges, and number of degree in the graph. However, G and H are not isomorphic. But you can see here that H has a circuit of length 3. So you can see here V1, V2, V6, V1, V1, V2, V6, V1. That's a circuit of length 3. But G does not have any circles of length 3. So G does not have any circles of length 3. Right? There's no circle of length 3 in G. Right? The smallest circuit G can have is circuit of length 4. There's no length 3 in G. So therefore, G and H are not isomorphic. See, that's another way to determine whether two graphs are isomorphic based on a number of graph, path, or circuits that you have. All right. All right. So that's another way to determine whether the two graphs are isomorphic. So you can use that logic to make the argument when you do the exam, or you can use a definition to show it. All right. Now we're moving on to 10.5. 10.5 focus on two famous graph, which is Euler and Hamiltonian's graph, right? Euler is famous for a lot of things. So we're gonna have Euler circus and Hamiltonian circus. So here are a few problems that you can try for your homework. So Euler path and circus. So the story begins in the town of Konigsberg in Russia, now known as Kaliningrad in Russia. So it was divided into 4 sections by the branches of the Pricho River in the 18th century, with 7 bridges connect the regions. So back in the day, people wonder whether it was possible to follow a path that crosses each bridge exactly once and return to the starting point, right? You can imagine, right? Back in the day, right? So they have to invent some game to play, right? So this is one of the game. So here is the image of the Konigsberg Bridge that we have. So we have 4 regions, A, B, C, D, as you can see, and they have 7 bridges connect the 4 regions. So they just wonder, okay, if I start at this bridge, can I go through all the region and go back to the same place exactly once without crossing the other one twice? Okay. Right. Remember, that's a very important keyword, exactly once, and return to the same starting point. I can pick any starting point and I can go through all the bridges exactly once if that's the case. So this is a kind of unsolved problem. People couldn't do it. So somehow it got to Euler, and then he got excited about it, and then he sit down and do a lot of try and error, and then he decided that there's no such path exists. All right. So yeah, so this is how he see it. So each of the region present a vertex, and then he can use the bridge as the edges connect to those. You can see here A and D, there's one bridge, there's one edge here. A and C, there's 2 bridges, so there's 2 edges. So you try to work on that model, and then based on that model, he tried to define whether it's possible or not. And the result is it's not possible, right? So it's not possible. So this is how he kind of prove it. So here is the definitions. An Euler circus in a graph is a symbol circus. Remember, it's a symbol circus that containing or visiting every edge of G, okay? Every edges of G, not the vertex, but the edges, okay? Because when they try to cross the bridges. An Euler path in G is a symbol path that containing every edges of G. So you can see the difference between circus and path, right? Circus, you go back to your original position, but not the path. They both have to be simple. So here are two examples. So let's see if we can play around with this. So which of this under the graph has an Euler circuit? Of those that do not, which have an Euler path. So if you have an Euler circuit, you will not have an Euler path. And if you have an Euler path, you're not going to have an Euler circuit. Okay, only one kind of curve, not both. So that's a specialty of Euler circuits. So yeah, you can see here, right? So let's see if we can see if there's an Euler path. Here are Euler circuits. So let's see, we pick B. Remember, we try to cross the edges one, not the vertex. So I can go to here, I can go to there, 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 and I'm stuck because I still have two edges that untouched, right? BE and then AB. So let's try again with another vertex, another approach. And I can start at D here. I can go there. I can go around. I can go around. I can go around. I can go back to this, and then I'm stuck. So yeah, we not cover everything. We're not cover every vertex or edges. So this graph does not have Euler circus or Euler path. So let's moving on to this guy. Let's see, right? So start from A, go to B. You can go to this one right here. You can go back to this. You can go back to that. You can go back to here. You can go back to this guy. You can go back to this one. You can go back to that. You can go back to that, and then you can go back to this. This you end, right? You start at A, right? We start at A, and then we end at D. Right? So all the edges are visited, but we not go back to A. So this one does have an Euler path, but it doesn't have Euler circuits. All right, so this one here, no Euler circuit. Also no path. This one here, no circuits, but this is a path. Right, so as you can see, that's travel of that, right? So you go A to B to E to C, back to E, and then to D, and then to B, and then back to E, and then back to A, and then C, and then D. Right, so you can go through the vertex multiple times, but you only worry about the edge that it only touches one time. Right? Okay, so is there a better way for us to decide whether it's have an Euler circuit or a path? Well, of course. This is why Euler is super amazing. Right? He actually proved it. That's what we call Euler circuits. So now, this is theorem, right? It said a connected multi-graph with at least two vertices has an Euler circuit if and only if each of its vertices have an even degree. Very nice, yes? The graph have Euler circuits if and only if each of the vertices has to have an even degree. Very important. And it's have an Euler path if and only if exactly two vertices of odd degree, and everything else have to be even. Okay, everything else has to be even. Okay, it only have exactly 2 vertices of odd degree, and everything else has to be even for it to have an Euler path. To have an Euler circuit, every vertex have to have an even degree. So we go back to the previous 2 examples. This is degree 3, this is degree 3, this is degree 2, this is degree 3, this is degree 3. So yeah, so odd degree. So no circuit. How many odd degree do we have? We have 4 odd degree vertices. So no path either, according to that theorem. And in fact, we did not have any circuits or path. This one here, and you can see degree 3, degree 4, degree 4, degree 3, and then degree 6. Of course, it's no circuit, but it had exactly 2 odd degree. So degree 3, degree 2, exactly 2. That's why we will be able to find the path. That's the amazing thing about Euler. Okay. So let's see if those graphs have Euler circuits or not. All right, degree 2, degree 3, degree 2, degree 3. So no circuits, but path, because it has exactly 2 vertices of degree 2, a degree of odd degree. Okay, so this guy degree 3, those are only 2 that have that. So in fact, yes, you can see here that, okay, I can start at A, or I can start at B, I can still go back to that, right? So let's see, we start A here, we go back to that one, we go back to that one, and oh, so we must have start at the odd one to, to do that. So we start from here, you start from here, you start from there, and then you go back to there, and then you go back to that. Okay, so we start at D. So you have here is A, not A. You have D, you have C, and then you go back to B, and then you go back to D, and then you go back to A, and then B. It's a path. All right, simple path, but not a circuit. You can see. All right. So here's the hint, right? In order to find a path, it's better if you will find a path if you start at the odd vertex with the degree. Okay. So you can see how when I start at A, I couldn't be able to find the path, but if I start either B or D, I will be able to. So that's how we write out the path. All right. So this one here, degree 2. This one 1, 2, 3, 4. So this is degree 4. 1, 2, 3, 4. Degree 2. 1, 2, 3. 1, 2, 1, 2, 3, 4. So that's degree 4. All right, 1, 2, 3, 4, and then 1, 2, 3. So same thing here. No circuit, because we have 2 vertices of odd degree. All right, so yeah, so we do have path. Yes, right, because it has exactly 2 vertices of odd degree. Okay, so that's the idea we can have. All right, so this one here, degree 3, degree 3, degree 3. So you can see no circuits or path are necessary for that. All right. So that's how we determine an Euler circuit and Euler path. Very easy. All you have to remember is that theorem. Okay, that Euler was proving. So that's why Euler is genius. Just one simple problem, and he could take it to the next level. And if you study more deeper in math, you can see there's a lot of Euler application that you can see. All right. As I said before, G1 just have an Euler path. Same thing with G2 on that. All right. So that's the path you can see. And G2 have 6 vertices of odd degree, so there's no Euler path or Euler circuits. Okay, if you have an Euler path and you don't have an Euler circuit, you have an Euler circuit, then you don't have an Euler path. That's the idea. All right, so next is we look at another example here. You can see. Okay, so now let's see if you can have an Euler circuit and an Euler path. All right, so 2 here, 1, 2, 3, 4 here, 2 here, 1, 2, 3, 4 here, 2 here, 1, 2, 3, 4. There's a 2 here, 1, 2, 3, 4, and then 1, 2, 3, 4. All right, so all even degree vertices. So it has Euler circuits. That's it. So when I have an Euler circuit, it doesn't have an Euler path, right? It's only one kind of curve. All right, let's see. So let's say we pick A, then we go to B, and then you can go to C, you can go to F, you can go to I, you go back to that one, you go back to F, go back to this one, go back to this guy, go back to this guy, go back to that guy, go back to this guy, go back to that, to this, and you go back to A. So that's an Euler circuit, right? So you start at A, you go back to A. So what? Okay, let's list out the circuits that we have. So we have A, we travel B, when you travel to C, we travel to F, we travel to I, we travel to H, we travel back to F, we travel to E, we travel to H again, we travel to G, we travel to D, we travel back to E, we travel back to B, and then travel back to D, and then we travel back to A. So that's the idea. You can go through the vertex multiple times if you want, but you only travel the edges one. All right, so let's start that again so you can see. All right, so here we go. We go to A. We start with A. So we go to A, and then we go to B, and then we go to C, and then we go to F, and we go to I, and then we go to H, then we go to back to F again, and then go back to E, and then go back to H here, and we go to G, and then we go to D, and we go back to E, and then E back to B, and then B back to D, and then E back to A. So we are back to A. And you can see that we cover all the vertices, all the edges exactly once. There's no overlap between any edges. All right. Now, Hamilton path and circuits. Now, Euler circuit, we expect to travel every edges once. Now, Hamilton's, we expect to travel every vertices exactly once. That's the difference, okay? A simple path in the graph G that passes through every vertex exactly one, we have ourselves a Hamilton path. And if you go start at this vertex and then go back to it exactly once, we call that a Hamilton circus. So remember, Euler focus on travel through the edges once. Hamilton focus on travel through the vertex exactly once. That's the two different things. All right, remember that. All right, so which of these have Hamilton path or Hamilton circus? All right, so let's see, pick a vertex. Remember, we only focus on the vertex exactly one. So I can go B to C, then I can go C to D, and go D to E, and go E to A, and I can go A to B. Yes. So yeah, let's have Hamilton circus. So B, C, D, E, A, and B. Okay, Hamilton circuit, you only worry that I only travel through the vertex exactly one. You can see that, right? So 1, 2, 3, 4, 5. Travel every vertex exactly one. Can I have a path? Yeah, so if I erase the connection between A and B, I do have a path. So B, C, D, E, and A. So I also cover every single vertex, but I'm not go back to B. And that's why it's a path. So you see the difference here? With Euler, you only have a circus path. You cannot have both. But Hamilton, you can have a circus and a path together. That's the difference. Because in Hamilton, you only worry about, do I cover all the vertex? I don't worry about the edges. That's the difference, okay? So there we go, right? So it's have Hamilton circus and also have a Hamilton path. That's just one of the example. So for this second example here, let's see if we can have a circus or not, right? So pick A again. So again, we only worry about, I cover all the vertices. All right, so I do go back to A. So I start A, B, D, E, C, and then A. So I also have a Hamilton circus. And if I erase the edge here, I also have a Hamilton path. All right, so I travel all the vertices, and then I can go back to that one. But what happened here? This one here, you can see that is not a symbol graph. So Hamilton only focus on a symbol graph or a symbol circuit. Yes. So therefore, watch out for those. So if you only consider a symbol graph, then this one is the only focus that we have. So you might wonder, is there a definition or a theorem similar to Euler circus that a guarantee? The answer is no. So for Hamilton, there's no theorem that guarantee that you will see circuits or a path. So we just kind of play along, say, tracing and figure out whether it works or not. However, it does have some theorem, but it's not uh, as solid as the other one. So we have here two of those, direct theorem and Euler theorems. And direct theorem said, if G is a simple graph with n bigger than 3 vertices, such that the degree of every vertex is bigger than n over 2, then G has an Hamilton circuit, right? So the degree of every vertex is bigger than or equal to n divided by 2, then G has a Hamilton circuit. And our theorem said G is a simple graph with n bigger than 3 vertices, such that degree of U plus degree of B is bigger than n for every pair of non-adjacent vertices, then G has an Hamilton circuit, right? So those are the two theorems that was not developed by Hamilton, but been taken over by Dirac and or kind of supporting the idea, but it's not necessarily true on that, right? So that's not a solid 100% sure like Euler theorems, all right? You can see here that G, H, and I, those are the three graphs. So let's go back to this. All right, if n is bigger than 3, then degree of every vertex is bigger than n over 2, then G of Hamilton circuit. So you can see here, how many vertices do we have? We have 1, 2, 3, 4, 5. So n equal to 5. So n over 2 equal to 5 over 2. So degree of this is 2, degree of that is 1, 2, 3, 4, degree of that is 3, degree of that is 3, degree of that is 2. But you can see here, degree of vertex A and vertex C is not bigger than n over 2. So what does that mean? So according to this one here, it said if every degree of every vertex is bigger than or equal to n over 2, then G is sure has a Hamilton circuit. So it doesn't say anything that what if it doesn't follow, then can we still have Hamilton circuits? You can see here, can we still have Hamilton circuits? So Dirac theorem does not apply, all right, because degree of A is less than n over 2, okay? But can we still have Hamilton circuit? So we start at A, we go to B, we go to C, we go to D, we go to E, we work to A. But we still have the Hamilton circuit. So A, B, C, D, A. What does that mean? It means that if a graph satisfies those two theorems, if the graph satisfies those two theorems, then you are guaranteed to have a Hamilton circuit. But if the graph does not satisfy those two theorems, then we can still find Hamilton circuits. Okay, so that's the idea. So it's not like rigid theorem compared to Euler circuits. So Euler circuit said, yeah, you don't have all the vertex have even degree, then you guarantee you have no circuit. This one here, there's no guarantee. That's why we don't have a Hamilton theorem. We have a Dirac theorem and Euler theorem. So those are the two mathematicians who continue to work on Hamilton circuits and give them necessary condition, but not needed. Okay. All right. So that's one of the example. Okay. So the famous for Hamilton path and circuit is the traveling cell persons. So in other words, right, if you travel to every city exactly once, right, you can go from Cali to New York, and then you can go from New York to Denver, Denver to Chicago, right? You travel around the city exactly once. So that will give you a Hamilton path. So, you know, think of this like, you know, when you book a around the world tour ticket, you can go to multiple cities like London, Paris, and then like Australia, things like that, and you're back to US. So that's Hamilton circuit right there. You travel a city exactly once. Okay, so that's a very famous example for computer science, traveling salesperson problems. All right. Okay, so that's the end of these two sections. I will see you on the next two sections.